Okay, 3.2, number 9. You're given a function which is f of x, and it is 2x squared minus 3x, 2x squared minus 3x plus 1, and it's on the interval from 0 to 2. Okay. Okay, so the question is verify that the function satisfies the hypothesis of mean value theorem, and then find the values of C which satisfy the conclusion of mean value theorem. So what are the hypotheses of mean value theorem? Well, is f continuous on the given closed bounded interval 0 to 2? And the answer is yes, because it's a polynomial function. 3, is f, let me say, does f prime of x exist for any x between 0 and 2? Again, the answer is yes. Okay. Again, because the derivative of a polynomial function exists everywhere, right? So the hypotheses of the mean value theorem are satisfied. So what's the conclusion of the mean value theorem? Think of this function as the position function of a moving object. Let's say the object is moving along this straight line. If this is the position function of a moving object, then over this time interval from 0 to 2, what's the average velocity? What's the average velocity over this interval? Well, the average velocity would be over this interval. How much displacement you have? The net displacement over this interval divided by the length of time, right? That's the average velocity. Length of displacement divided by net displacement over the interval divided by the length of time, right? So what's the net displacement then here? Well, it'll be f of 2, right? After 2 hours, what's the position? After 0 hour, what's the position? So the difference will give you the net displacement. And then if I divide that by 2 minus 0, that's the length of time over this interval. So that will be the average velocity, right? And mean value theorem says that this average velocity would be the same as the instantaneous velocity at some time c. So this is for some c between 0 and 2. So for some c between 0 and 2, the instantaneous rate of change, right? This is the derivative at c gives you the instantaneous rate of change at c. So the instantaneous rate at some point is the same as the average rate over the interval. Am I making sense? So again, the mean value theorem says the average rate over an interval, the average rate of change over an interval is the same as the instantaneous rate of change at some instant c in that interval. Okay. So we now have to solve for c, right? How do I solve for c? Well, what is f prime of x? Do we know f prime of x? Well, we have the function to be given by what? 2x squared minus 3x plus 1. So the derivative would be 4x minus 3, right? 4x minus 3. And so f prime of c would be what? 4c minus 3. And oh, by the way, what is f of 2 minus f of 0? Is f of 2 when you plug in 2 for the for x, what do you get? You get 2 times 2 squared, so that will be 8 minus 6, which is 2 plus 1, which is 3. So you get 3 here and 2 here. So now we have to oh, there is f of 0, I forgot, right? This is 3 minus 1. It's 3 minus 1. So this is basically 1 then, right? Okay, so then I can solve basically the derivative at c, 4c minus 3, and that's the same as the 1, right? And so what is c then? 4c would be 4. C would be 1. Did that make sense? Anybody has any question? I'll be asking one question from this section, okay? One question from this section for sure. 3-2. Rolle's theorem is a specific case of mean value theorem because Rolle's theorem has one more condition, right? Yeah. So I mean, you can think about if f of 2 and f of 0 were the same, right? F of 2 and f of 0 were the same, then wouldn't you get 0 here? So Rolle's theorem says the instantaneous velocity will be 0 at some point. Okay? So that's the difference. Yeah. So in fact, you can always just remember mean value theorem and don't worry about Rolle's theorem at all, because I mean, if you can apply Rolle's theorem in a problem, you can also apply mean value theorem. Okay? You get the same answer. Okay. Next question, anybody?
We did 13 on that.
13. Find the number c that satisfies graph the function. Okay. 13. You have f of x is root x. F of x is root x, and let's sketch the graph of that function. Okay, the graph of this function, well, let's say when x is 1, this is 1. When x is, so this is 1, 2, 3, and 4. When x is 4, the value of the function is 2. So the graph is let's say that's how the graph looks like. This is the graph of root x. We are going from 0 to 4 though, right? So all I have to look at is what is happening from 0 to 4. What does the mean value theorem tell us about this interval from 0 to 4? Remember I explained graphically what's the meaning of mean value theorem. So if I look at the over this interval, right? If I look at the extreme point 0 and extreme point 4 over that interval, let me erase this part here because we don't need that. So the mean value theorem, if I look at this point here and this point and join them with a straight line, so let's join them. What is the slope of that? What is the slope of that line? What's the slope of that line? Well, we need to know the coordinates here. What's the coordinate of the point at 4? Yeah, 4 comma 2, right? Because when x is 4, root x is 2, and the other point is 0, 0, right? So what's the slope of this line? What's the slope of this line? Let me call that line S. So what's the slope? What's the slope? Slope of S. Yeah, you subtract 2 minus 0 divided by 4 minus 0, right? You subtract the second coordinates and then divide by the difference of the first coordinates. So that's what, half, right? Okay. And the mean value theorem says that mean value theorem says that this slope is the same as the slope of the tangent at some point here. So the slope of this line is the same as the slope of some tangent line here. That's what it says, because this slope represents, the slope of S represents the average rate of change over this interval. Because this is the average rate of change, okay, over this interval. The slope of S is the average rate of change, and when we look at the slope of a tangent here, that's an instantaneous rate. The slope of a tangent is an instantaneous rate. The slope of S is the average rate. So let's apply the mean value theorem. I'm not going to, is this function continuous over the interval from 0 to 4? Yes. Is it differentiable between 0 and 4, not including 0? It's not differentiable at 0, right? This function is not going to be differentiable at 0, because if you take the derivative, what do you get? What's the derivative of this guy? 1 over 2 root x, right? Obviously, the derivative does not exist at 0. But we don't care at 0, right? The condition in the mean value theorem is that does the derivative exist between 0 and 4, excluding 0 and 4, right? And that's the case. Yes, this derivative does exist for any value of x, which is greater than 0, right? So the hypotheses are satisfied. The next thing that I have to check, now I don't have to check any more things. Now I have to apply the mean value theorem. So the mean value theorem says there is a value of c where the derivative is equal to the value of the function at 4 minus the value of the function at 0 divided by 4 minus 0, right? So this is the average rate of change over the interval from 0 to 4. That's the same as the instantaneous rate at c. And for some c between where c is between 0 and 4, right? For some c in that interval. And f prime of c is then what? 1 over 2 times the root of c, right? Because the derivative is 1 over 2 root x, right? So f prime of c would be that. And what is f of 4 minus f of 0? Well, that's 2 minus 0 over 4 minus 0, as we saw before, and which is half, basically. And how do we solve for c then? I get 1 over 2 root of c is half. Multiply both sides by 2, you get 1 over root of c to be 1. And is it clear that c has to be 1? Or you can take the reciprocal, right? This is like having 1 over 1, right? This is like having 1 over 1. So if I take the reciprocal on both sides, I get root of c to be 1. right? And then if I square both sides, I get 1 still, right? So C has to be 1. So I go back to my picture here. I see that the slope at 1 is the same as the slope of S. So let me draw the slope at 1. So this is the point at 1. The slope at 1 is the same as the slope of the line S. Okay, so that's what they asked you to do, to sketch and show the meaning of mean value theorem graphically. Is that making sense? Okay. Anybody is having trouble writing it down? All right. Next problem. 7 where? 7 3.2. I am not going to sketch the curve for you, okay? What you have to do is look at the point at 0 and the point at 8, okay? Look at the point at 0 and the point at 8. Join them by a straight line and find the slope, okay? You don't have to find the slope. Then you want to find points on the graph where the tangents are parallel to that line. Am I making sense? What's the point at 0? 0, 0. What's the point at 8? The point at 8 is 3, right? 8, 3. Join those 2 points with a straight line. Join the 2 points with a straight line on the graph, and then try to approximate points on the graph where the tangents are horizontal to that. Am I making sense? So your answer would be approximate position of those tangents. Okay, so I won't do it. Any other questions? So again, let me just say one more thing here. What they are saying, you have a graph, and you have the end point, the beginning point, you add them. Okay, and then you approximately find the points on the graph where the tangents are parallel, okay? So maybe here the tangent is parallel like this, okay? So you're asked to find these points, okay, approximately. Okay. Any other questions? Should we move on to 3.3? Go to 3.3.
Number 9, please. On 3.3.
Number 9.
Yep.
Okay. Number 9, 3.3. You're given a function which is 2x cubed. The function is 2x cubed plus 3x squared plus 3x squared minus 36x minus 36x. Okay, you have to find the intervals. Okay, so pretty much you have to do everything. You have to find where the function is increasing, decreasing. You have to find where the function is concave, up and down. You have to identify the inflection points and so on. And you have to identify the local max, local mean. All right, so we know the steps. Basically, remember when I showed you the steps for sketching the curve? There were 2 steps, right? One was increasing, decreasing. The other one, you have to basically do those 2 steps here. So what do I have to do? So let's do in this case, let's do where the function is increasing and decreasing first, okay? So for that, we need to find the derivative. And what's the derivative in this case? What's that? 6x squared plus 6x minus 36. And since we have to also find where the function is concave up and down, let's find the second derivative as well. The second derivative would be what? 12x plus 6. Okay, now we have to find the values of x where the derivative is 0 or does not exist, and find the values of x where the second derivative is 0 or does not exist, right? For concavity. So let's just find first of all where the derivative is 0 or does not exist. But in this case, because I have a polynomial function, the derivative exists everywhere, so I don't have to worry about finding points where the derivative does not exist, right? So the first thing I'm going to do is solve f prime is 0 and f prime of x does not exist. So find points for which f prime does not exist. As I said, there will be no solution in this case. No solution in this case. So that's why I'm crossing that out. Okay, now the derivative is 0. So that means what? 6x squared plus 6x minus 36 is equal to 0, right? If I factor out a 6, I get x squared plus x minus what? Can you factor that out? X plus 3, x minus 2. Since I am going to write the factorization here as well, that's going to help me determine the sign of the derivative. So I'll keep that 6x plus 3 times x minus 2. That's the factorization of the derivative. Alright, so that means the critical points are what? Negative 3 and at 2. Is everybody okay with that? Now, since I have no points where the derivative doesn't exist, so these are the only two critical points, and I'm going to make my number line here now. What's the domain of our function? Yeah, the domain of our function would be all real numbers because it's a polynomial function. It's a polynomial function. So and in the domain, I'm going to plot the point negative 3 and the point 2. These 2 points divide the domain into 3 subintervals. What's the sign of the derivative function on the left of negative 3, between negative 3 and 2, and on the right side of 2? That's what I need to figure out. And I have the derivative right in front of me right here. This is the derivative, in fact, right? So when x is less than negative 3, I have, this will be positive, right? You guys see that? This will be positive. And when x is between negative 3 and 2, you get negative here because they have opposite signs. And when x is bigger than 2, obviously everything is positive. Okay, so then it means that, so this is the sign graph for the derivative f prime. So that means my function f, what is happening to the function f then? The function f is increasing here, decreasing here, and increasing here. Are we okay with that? And can you tell me where is the local max, local mean? Very good. Local max here local mean at 2. Okay. Okay, so that's one part is done. Now we find out where the function is concave up and down. Yeah. Plug -3? Why -3? We know that at -3 the derivative is 0. -3 is the critical point, right? So we found -3, at -3 the derivative is 0 already. I think you're talking about plugging in like -4 or -5 to know what's the sign of the derivative, right? Oh, you to find the points. Oh yeah, we're gonna do that later. Excuse me. We're gonna do that later if we have to sketch the graph. Yeah. Okay. Okay. Now we need to find where the function is concave up and down. For that, I need to solve what? Solve the second derivative is 0, and the second derivative does not exist. Again, I have no solutions here, so all I have to find out where the second derivative is 0, and it is 0 when the second derivative is what? What was the second derivative? 12x 6. Was it plus or minus? Yeah, plus 6. Okay, so then x would be what? -half. Okay, so then draw again. If I look at the domain of the function, and let's say half is here, that's the only point where the second derivative is 0 or doesn't exist. -half, sorry. And so what's the sign of the second derivative on the left side of -half? Well, yeah, when x is, for example, -1, you see that it's negative here. And on the right side of -half, for example, if you plug in 1, you see that it's positive. Right? Is everybody okay with that? And so the function f, yeah, go ahead. The function f is concave down here, concave up here. Yeah. Yeah. Second derivative. Yeah. To know where the function is concave up and down, you look at the second you find out where the second derivative is 0. So we found out the second derivative is 0 at -half. You also find out where the second derivative does not exist. But in this case, the second derivative exists everywhere. So that's the only point. Now you pick a point on the left side of -half, like -1, and plug that in the derivative function, second derivative function, and see if the second derivative is positive or negative. Right? So you're trying to find out where the second derivative is positive and where it is negative, and depending on that you can say that f is concave up and down here and here. Yeah, the first derivative tells you where the function increases and decreases. Second derivative tells you where it's concave up and down here. Did I make a mistake?
-1, that would make it plus 36 at the end.
No, this is the derivative, right? This is the derivative. So when you plug in -1, wouldn't you get negative? So remember the second derivative this was the second derivative, right? So if you factor out c, you get 6, you get 2x plus 1, right? And when x is something like -1, it's negative, right? Okay, so we got where the function is concave up and down as well. What are the inflection points? Well, since the concavity changes at -1/2, that's the inflection point, right? So -1/2, I have an inflection point, meaning that the concavity changes there. I guess that's all it was asking us to find, okay? In this question, they were not asking us to sketch the graph. Okay, that's all they were asking. I'll discuss about the language of the exam once we go through this question answering part. Yeah, I have something that I want to do at the end.
The answer, and it does say it's concave up.
The answer says concave up to -1/2.
From -1/2 to.
It's concave up.
I'm reading it.
Yeah, it is from -1/2 to infinity, right? Yeah, that happens. Sometimes it happens to me as well. Any other questions? 27. Okay, 27, again, you have a graph there, right? On what intervals is f increasing and decreasing? It's pretty clear, right? If you look at the graph of, so you are given the graph of the derivative function, right? So wherever the derivative function is positive, right, the function f will be increasing there. Wherever the derivative function is negative, so make a number line and make a sign graph for the derivative function from the graph, and then decide where the function is increasing and decreasing, right? Am I making sense? Because you are given the derivative function, can't I say by looking at the derivative function, I can say that the derivative function is positive between 0 and 2, it is negative between 2 and 4, it is a positive between 4 and 6, and between 6 and 8 it's negative, and after 8 it's positive, right? So make that sign graph on the number line, and then wherever it's positive, the function f would be increasing, wherever it's negative, the function would be decreasing. So you're given the graph of f prime, not f here, right? Am I making sense? You're given the graph of f prime. So the sign of f prime tells you something about the function. Is that making sense? Right. Once you make the sign graph like the way I did here, right? Once you make the sign graph, then you can say which one is the local max and which one is the local mean, and so on, right? Okay, the derivative doesn't exist at 6, so you have to consider that. You have to consider that as a point where the derivative doesn't. You have to consider 6 as a critical point. Note that the function it's in the problem, it tells you that the function is continuous at 6 also, even though the derivative doesn't exist at 6. Right? From the graph, I see that the derivative does not exist at 6, right? Because you have a hole, right? But the function f is continuous there. You can see what to do, or should I say anything anymore? Okay. Any other questions from this section? 35. X root of 6 minus x. 35 is x root of 6 minus x, and it's capital F of x. Okay, I am going to rewrite this as x times 6 minus x to the half. Okay, now we have to basically what? Sketch the graph of this guy? Yeah, pretty much you have to do the things that we have done before, and then we also have to sketch the graph. Yeah. Okay, so what do? Well, we find the derivative. Well, since we have to find the graph of this, let's go through all these steps, okay? Not just the steps they specified. The first step is what? What's the domain? What's the domain of this function? Well, the only restriction I have is that 6 minus x has to be what? 6 minus x has to be, so let's do some scratch work here. 6 minus x has to be larger or equal to 0. So 6 has to be larger or equal to x, which means x is less than or equal to 6. So the domain would be what? That's the domain. Is everybody okay? Well, what's the second step? What was the second step that I said? Second step I said terminal behavior, right? What's the behavior of the function near 6? What's the behavior of the function at negative infinity, right? So how do I figure that out? Well, I have to look at the limit as x goes to 6, but x can go to 6 from right or left? Left. Of this function x multiplied by root of 6 minus x. And what is that limit? What is that limit? Zero, right? Shouldn't take that long, okay? You have x there, the limit of x is 6, the limit of root of 6 minus x when x goes to 6 is 0, right? So it is 0. Okay. What's the limit as x goes to negative infinity of x times root of 6 minus x? What is this limit? It should be pretty easy to say. Was that? Yeah, so look at what's going on here, right? As x goes to negative infinity, what is happening to what is inside the root? Well, forget about the 6 here. What is happening to negative x when x is going to negative infinity? Negative x is going to positive infinity. So root of that will go to positive infinity. This guy is going to negative infinity. So one factor goes to negative infinity, one factor goes to positive infinity. So that means one factor is becoming large negative, another factor becoming large positive. So together, the product would be negative large, right? So it'll be negative infinity. Did that make sense? Okay, so that's the second step. What's the third step? What was the third step that I wrote? Intercepts, maybe? Okay, so how do I find it? What is it? The easier? Which one is the easier? Find the y-intercept, right? How do you find the y-intercept? Yeah, we just did. What we said is that when x goes to negative infinity, the limit is negative infinity. That tells you there is no horizontal asymptote. And in this case, when x goes to negative 6, the value goes to 0. So in this case, we see that we don't have the vertical asymptote as well. If we had one, we would know. If this limit was negative or positive infinity here instead of 0, then you would have a vertical asymptote. So none of them here. Y-intercept, you let x to be 0, right? So well, what's the value of y then? So y is f of x, and then if you allow x to be 0, you get y to be f of 0. And what is f of 0? Why am I using lowercase f's? I'm sorry. I think the function is uppercase f, right? Uppercase f. And what is f of 0? That's 0, right? Is everybody okay with that? Because when you plug in 0 for x, you get 0 times root of 6 minus 0, right? So what's the y-intercept? 0, 0. What do we do about the x-intercept? For the x-intercept, I have to solve for x, right? By setting y to be 0. So then f of x is 0, and what is that? X times root of 6 minus x, right? And when is this 0? X times root of 6 minus x, right? Isn't it? Yeah. So when is it 0? Well, 0 or 6. X is 0 or x is 6. So the intercepts would be what? When x is 0, we already know that y is 0. So that's one. We already know that intercept. And the other one would be when x is 6, y is what? 0. Because we are trying to find the y-intercept, right? So that's 0. So okay, so x-intercepts, there is an intercept at 6, 0. Okay, we're done with the intercepts. What was the third step? I think now we find increasing, decreasing, right? Okay, where is f increasing and decreasing? Well, we have to find the derivative of the function. What is the derivative of the function? This is x times 6 minus x to the half, and I have to apply the product rule to find the derivative, right? So if I apply the product rule, the derivative of x is 1 multiplied by 6 minus x to the half plus x multiplied by the derivative of 6 minus x to the half, which would be half 6 minus x to the what? Negative half. But don't forget to multiply by negative 1, because that's the derivative of 6 minus x, right? Is everybody doing okay with what we did so far? So this is 6 minus x to the half minus, let me write it as half x 6 minus x to the negative half. Is everybody okay with that? These calculations are okay to you? Okay, how do we simplify this? There are a couple of things that could be done. One thing we could do is we can factor out the negative exponent 6 minus x to the negative half. If I factor that out, what would I get? In fact, let's factor out the half too. If I factor this out, what do I get? Remember what I said? If you are factoring out something, then inside the brackets, you divide each term by what you are factoring out. So if you divide this by what you are factoring out, what do you get? What do you get when you divide? So what I'm saying is, let's do some scratch work. If I divide the first term, 6 minus x to the half, if I divide that by half 6 minus x to the negative half, right? What do I get? I get 2 because of the half, and I get 6 minus x to the half minus half, which is 1, right? So I get 2 times 6 minus x to the 1, and then here I would be getting half goes away, and so all I get is x there, right? Because 6 minus x to the negative half is what I factored out. I factored out the half, so x is remaining there. You guys are okay with that? So this is going to be half. I am going to write this negative exponent now in the denominator as half 6 minus x to the half, and inside the brackets, what do I have? 12 minus 2x minus x. So what is that? 12 minus 3x. So at the end, then I have 12 minus 3x divided by 2 times 6 minus x to the half. Everybody is okay with that? Okay, so that's the derivative, right? Is everybody done writing it down? Done? Okay, now in order to know where the function is increasing and decreasing, what I have to do is I have to solve, go up. So solve where the derivative is 0 and where the derivative does not exist, right? The derivative doesn't exist where? When x is what? Huh? The only place, I mean, looking at the derivative formula, the only value of x where the derivative doesn't exist is 6, right? When x is 6, right? And however, that x equals to 6, that point is the end point of my interval, okay? So I don't have to worry about it. Am I making sense? The derivative doesn't exist at x equals to 6, okay? But this is the end point of the domain, end point of domain. So we don't really have to worry about it. What is the if the derivative is 0, then what is true? Looking at the derivative fraction, that means the numerator needs to be 0, right? So 12 minus 3x would have to be 0, and so that tells me x is what? X is 4, right? X is 4, everybody? Okay. So now I make my domain picture. So I have, let's say that's my domain. That my domain is not everything, right? What's this point here? That point would have to be what? 6. What is the critical point that I obtained? 4, right? So I plot that. Now I have to decide where the derivative function is positive and negative. If you look at the derivative, right, the denominator is positive. Why? Because it's the even root, right? It's the positive even root, right? So because x is less than, so this is the positive in the denominator. So all I have to see whether the numerator is positive or negative. And what can I plug in? To the left of 4, yeah, the easiest thing to plug in is 0, right? So if I plug in 0, clearly it's positive. So positive, positive, positive. And if I plug in something to the right of between 4 and 6, for example 5, clearly I get negative. So what we have then is, so this is the sign graph for the derivative, and the function f then is increasing up to 4, and then it decreases after that. And so at 4, what do we have then? We have a local max at 4. Everybody is done with the picture? Okay, now what do I have to do? Yeah, I have to find the second derivative now, right? Second derivative. What's the second derivative? So this is the derivative, right? 12 minus 3x over 2 times that. So I have to square the denominator. So what do I get if I square the denominator? I get 4 times 6 minus x. Here I'm going to get 2 times 6 minus x to the half. Multiplied by the derivative of the numerator, which is what? Negative 3 minus numerator is what? 12 minus 3x multiplied by the derivative of the denominator, and the denominator was what? 2 times 6 minus x to the half, right? So the derivative would be 2 times half, and so that will be going away, and you get 6 minus x to the negative half, 6 minus x to the negative half, and then you also multiply by the derivative of negative x, which is negative 1. Okay. How do we simplify this? We do the same trick as before. First of all, notice that this negative 1 and the negative here would become a positive, right? Let's do the following. Let's factor out 6 minus x to the negative half only. So from the first term, what do I get? I get a negative 6 because 3 times 2 is there, and then 6 minus x to the what? We did this before, right? When you divide 6 minus x to the half by 6 minus x to the negative half, you get 6 minus x to the positive 1, right? 6 minus x to the half divided by 6 minus x to the negative half. You're going to get 6 minus x to the 1. Minus, it will be a plus because of the minus 1. And I get 12 minus 3x, right? 12 minus 3x. So this will be 4, 6 minus x here. Okay, so then inside the brackets, what do I have? Minus 36 there plus a 12, right? So what is that? Minus 36 plus a 12. Negative 24. And then I also get a plus 6x, right? Plus 6x minus 3x, so that's what? plus 3x. I am going to combine the 6 minus x to the negative half with the denominator 6 minus x. And if I combine them, what should I get? 3 half. Because 6 minus x to the negative half is the same as 1 over 6 minus x to the positive half. And then when you multiply them, you get 3 half. Okay, so we simplified the second derivative. And now it looks pretty simple. So now I have to solve. Second derivative is 0. And second derivative doesn't exist, right? Once again here, all I'm going to get is that x is 6. Again, it's the endpoint here, so we don't care about that. So if the second derivative is 0, then I get negative 24 plus 3x is 0. And so x would be what? X would be 8. Once again, we make a picture. The sign graph for the second derivative, this would be 6, right? And we have to, oh, wait a minute. Yeah, notice that this is not in the domain of the function. What does it mean then? It means that the sign of the second derivative would be what? The same everywhere, right? Well, what's the sign then of the second derivative? It's 24 minus 24 plus 3x, right? So we see that it's always negative, right? Everybody is okay with that? Because x is less than 6, yeah, so it's always negative. It's always negative. Which means it's concave down. So f is concave down. Okay, we have the increasing, decreasing concavity and all that. That was part what? I forgot. What was the part? We found out where the function is increasing and decreasing. That was step 4 or 5. I think this should be step what? 5. Yeah. Okay, now it's time to sketch the graph, right? Why don't you do it on your notes and see if you can come up with it now. Oh, well, there is one more step though, right? You have to find out the values of f. This would be step 6. Find the values of f at the critical points, the x-intercepts, you have to plot them. So what is the value of the function f at the what critical point did I get? There was only 4, right? At 4, what's the value of the capital F function? When x is 4, it will be 4 times root of 6 minus 4, right? So 4 root 2. And remember, we have the intercepts, right? We have the points. So I get the point here. 4 comma 4 root 2. That's 1 point. I have the intercepts are what? 0, 0. I have the intercepts at 6, 0, right? Right? Okay, so plot them first. And then sketch the graph, okay? Plot these points first. What is the function here? X is less than 6. It has some negative values here. Okay, this is my x-axis. And that's my y-axis. I have the point at 0, 0. The point at 0, 0. I have a point at 6, 0 and 4, 4 root 2. What is 4 root 2 approximately? 5.6, okay. We have to decide on a scale. Let's say this is 1 here. This is 2, 3, 4, 5, and 6. So let's say 6 is here. So remember, I get the point at 6, 0, right? At 4, what point do I get? The height would be at 4, the height would be 5, right? 2, 3, 4, 5, 5 and a half. So something like this is what I get. Now you ask yourself the following question. You sketch the graph from, say, left to right. On the left side of 0, what is happening? Is the function increasing or decreasing on the left of 0? On the left side of 0, is the function increasing or decreasing? Anyone, can you look at the graph? Is the function increasing or decreasing? It's increasing. The function is increasing all the way up to 4, right?
Yes.
So it is increasing to the left of 0. And then is it concave up or down? Down. So I know that the curve is coming from down. Below. Oh, we also know that as x goes to negative infinity, the function is at negative infinity. The value is negative infinity. So I know that the graph is coming from down, and it's going to be a curved concave down, and then it's going to go all the way up to 4, right? And it is in fact concave down all the way through, right? And what is happening after 4? It's decreasing, right? So I think it's pretty clear what's the graph, right? It would be, if I can make yeah, so the graph would look like this. Everybody agrees with that? Okay, I mean that's a good practice on graphing. A lot of work when you computed the only difficulty here that we faced here was finding the first derivative and the second derivative and simplifying them. Otherwise, everything else were pretty easy. Okay. Yeah. Yes. You're here? Where?
Yeah.
Second derivative? Okay, what time is it? Let's take 5 minutes, okay? When we come back, I will sort of discuss a little bit about the exam and sort of tell you about how the problems will be phrased, okay?